Hello everyone, this is Miss Lindsay. Today we're going to be talking about section 12.3 Exponential and Logarithmic Relationships. Let's recall converting a logarithmic function into an exponential function. So here we have log base a of x equals b. That is equivalent to a raised to the power of b equals x. And this is true for any positive a value. We also have a couple properties. And these properties hold true because we know exponential and logarithmic functions are inverses of each other, and we'll talk about this later in the notes. The first one is a raised to log base a of x, and please notice that entire log portion is in the exponent. That would be equivalent to x. And the second one is log base a of a raised to x would be equal to x as well. So let's go ahead and use these properties as we go through some of our examples. First, let's convert some exponential equations into logarithmic equations. So our first one is 6 raised to the 0 equals 1. Converting that to a log, so that would be log base 6 of 1 equals 0. And again, the base of the log would be also the base of your exponent there. 2 would be log base 10. Again, the bases are the same there. Of 0.001 equals -3. Now typically we would not actually write that base 10. It would simply be written as log of 0.001 equals -3. Either would be acceptable, but typically in the textbook you would not see base 10 written. So please go ahead and pause at this point in time, do problems 3 and 4, and then check your answers. Push play to check your answers. So 3, again, converting this to a log, that would be log base 16 of 2 equals 1/4. And number 4 would be log base 3 of 9 equals x. Let's go ahead and go in the reverse direction, taking a logarithmic and writing as an exponential equation. So here again, our base of 2 of our log would become our base of our exponent. So we have 2, come on over and get that 5, so 2 raised to the 5th. Equals 32. And please notice that is a true statement. 2 to the 5th power is equivalent to 32. Number 6, again, typically that 10 is not always shown in this, in the textbook, or in any textbook actually, but in this case, we went ahead and put that 10 in there. So that becomes the base of our exponent. Come over and get that -2, so 10 to the -2 equals 0.01. And again, that is a true statement. So at this point in time, I'd like you to pause again, and please try 7 and 8, push play to check your answers. So on number 7, we get 4 raised to the x equals 16. And on 8, we get m raised to the power of z equals y. On our next examples here, let's simplify. Using the property that we had from earlier, we had log base a of a to the x. If you notice again, those values, the a's, were equal to each other, the base of the exponent, the base of the log. So that simply would be equal to x. These bases would be the same, and again, that base 10 is not always written. In this example here, I went ahead and put that in there. But since those are equal to each other, the answer would be 3.2. Switching colors here for number 10, same idea with our property here. From earlier, we had a raised to the log base a of x. Again, notice the bases are the same there. That would simply just be equal to x. Same idea here, the bases of 4 are the same, so this simply would just be equal to 3. On number 11, notice there is no base there. It is 10. If you need to write that in there, that is fine. But typically it's not in there. We want to try to get 100 as written as something that 10 raised to what power? So again, we can apply that property that we just used in 9. So we know that we have log base 10 is equal to 10 squared. We know 100 is equal to 10 squared. So again, we get those bases to be the same. So that would be equal to 2. Go ahead and pause at this point in time. Try number 12 using that same idea that we did in number 11. and then push play to check your answer. So if we look at 12, again, our goal is to get this written as 3 raised to some power. Well, we know 3 raised to the half is equivalent to the square root of 3. So we can rewrite that as log base 3 of 3 raised to the half. So now we have those bases the same. So it'd simply be a half. Let's look at the next set of problems. Now we're going to be solving some equations. We have a logarithmic equation. Let's go ahead and use the exponential form of that. So we'd have x raised to the 4th power equals 81. Now we have an equation that we can solve. We take the 4th root of both sides to solve for x. We get x equal to 3. On 14, same idea. Let's convert this to exponential form. So 2 raised to the x equals 16. Now we got to think about 2 raised to what power would give me 16. 2 squared is 4, 2 to the 3rd is 8. So if you said the answer is 4, you're correct. 2 to the 4th is 16. 15, same idea. Let's write that in exponential form. So 10 to the 4th equals x. If we go ahead and solve that, we get x equal to 10,000. 16, we have to be a little bit careful on this one. Let me go ahead and switch colors here. We have the base is 2x, so we have to make sure when we raise that to the negative 2 power, we raise the quantity 2x to the negative 2 power. Let's go ahead and simplify that. Get rid of our negative exponent. So that becomes 1 over the quantity 2x squared, which becomes 1 over 4x squared. At this point in time, we can multiply both sides times 4x squared, so we'll get 1 equals 32x squared. I'll continue that up over here. Divide by the 32. And square root both sides. And actually, we should take plus or minus when we square root both sides. However, I'm going to cross off that plus or minus. Because with logarithms, we restrict the domain to values greater than 0. This allows us to have log and exponential functions be inverses of each other, so we only want the positive value there. Okay? So after we do that, we just need to simplify the square root of 1 over 32. Square root of 1 is just 1. Square root of 32 would simplify into, 4 square root 2. And then let's go ahead and rationalize the denominator there by multiplying the numerator and denominator by root 2. So we get that to be root 2 over 8 equals x. At this point in time, I'd like you to again pause. Please do number 17 and then push play when you're finished. So on 17, again convert this to exponential, so we'll have 2 raised to the 2nd power equals 3x plus 1. So we'd have 4 equals 3x plus 1, subtract over that 1, which will give us 3 equals 3x. So x would be equal to 1. Now let's go ahead and simplify each of the following. What I would suggest on this is pausing, again trying these problems 1 through 9, and then pushing play. So if we start here with 1, again our goal is to get that raised. We know that's base 10, so we want that to be raised to the 3rd power, because we know 10 to the 3rd is 1,000. So now we have our bases the same, which would just give us 3. On number 4, we have, again, rewrite that cube root of 4 as 4 to the 3rd. So now our bases are the same, and we get that to be a 3rd. On 7, there's a couple different ways to do this problem. I'm going to show you a slightly different way of doing this problem. I'm going to go ahead and just set that equal to x. Now I've made that into a logarithmic equation, and I'm going to write it as an exponential equation. So we can say, okay, 8 raised to the x equals 2. Well, in that case, we got to think about, it's not going to be 8 squared. We got to go something smaller. We got to think more of square roots, cube roots. And if you thought of a cube root, you're absolutely right. The cube root of 8 is 2. That way we know x would be equal to a third. Okay. Number 2. So we have log base 4 squared. Again, our bases are the same, so that would be 2. Go ahead and finish 5 through 9, and we can finish those in class. And you can check your answers in class to those problems, 5 through 9. At this point in time, or if you're in AAA, you can go ahead and push stop. If you're in AATH, please go ahead and move on to the next example. This next example, we're going to deal with the two properties that we talked about at the beginning of the lesson. We're going to actually prove why these are true. Okay, so our very first one that we're going to deal with, we're going to show that a raised to the log base a of x is equivalent to x. So let's go ahead and rewrite that. And right now it's in exponential form. So let's go ahead and take that and rewrite that in logarithmic form. So again, my base here is a, so I'd have log of a come over of x would be equal to log a of x. So at that point in time, you can see that we have two logarithms set equal to each other with the same bases. So if those are set equal to each other, we definitely have x equal to x. Okay? Therefore, we have just proved that is a true statement. And there is actually another way to show this using the fact that exponential and logarithmic functions are inverses of each other. And this is shown in the textbook. We can talk about that later in class. But I'd like you to use this exact same approach on number 1. And I would like you to try to do this for number 2. Okay? And again, we will discuss that in class and go over that answer in class. So at this point in time, we are done with section 12.3.